there, STEM chemistry students. This is Ms. Ruark, and we are here with Vodcast 6.1, where we're going to talk about what do we get out of a chemical reaction? Like, what is the reason that we balance a chemical equation, and what information can we pull from that? I know we've talked about it a little bit, but we're going to go a little more in depth in it now because we're going to be using the information that you get from a balanced chemical reaction to solve problems. All right, so we have this equation up here at the top of the screen. It says 4NH3 plus 5 O2s gives us 6 H2Os and 4 NOs. Okay, so what in the world does that mean? Well, that means that when we go to react these, that for every 4 ammonias that we react with every 5 oxygens. So for every 4 ammonias and 5 oxygens reacted together, we can make 6 waters and we can make 4 nitrogen monoxides. Okay, that seems pretty simple, right? Okay, well, as chemists, we like to use that funny thing called a mole. And we use it for all sorts of things. Well, here we're going to say for every 4 moles of, that's supposed to say NH3, not HN3. Sorry. For every 4 moles of NH3 and 5 moles of O2, then we can make 6 moles of H2O and 4 moles of NO. And so we use that, that's what we call our, we use this in stoichiometry, which refers to the relative quantity of moles, and we say that these are our mole ratios. So anytime I ask you, well, what's the mole ratio in this equation of ammonia to oxygen, you would say it's a 4 to 5 ratio. Well, what's your mole ratio of oxygens to nitrogen monoxides? Well, it's a 5 to 4 ratio. Okay, so you're just saying your ratio of how many each one you need to each one you'll make. Okay, so a balanced chemical equation is going to be kind of like a recipe. Okay, so let's say that we wanted to make sandwiches. Now, in this case, we're going to make cheese sandwiches. Now, some of you are like, oh, that's delicious. And some of you are like, what? Where's the meat? Right? Okay, I get it, carnivores. It's okay. We can make cheese sandwiches. It'll be okay. All right, so here it says predict how many cheese sandwiches as defined by the picture above you can make if you have 6 pieces of, I made all sorts of typos in here, 6 pieces of bread, wow, sorry, and 4 slices of cheese. So if we have 6 pieces of bread, if we have 6 of these, and we have 4 of these, how many pieces or how many sandwiches can we make? Well, we need 2 bread and we need 1 cheese for each sandwich. Well, I have 4 pieces of cheese. That means I can make 4 sandwiches, right? Not so much, because I only have 6 pieces of bread, which means the most I can make total sandwiches would be 3. Right? If I need to make 14 sandwiches, well, how many slices of bread would I need? Well, to make 14 sandwiches, each sandwich needs 2 pieces of bread, so I would need a total of 28 slices. Okay? So that would be our mole ratio here, a 2 to 1 ratio for every 1 sandwich that we make. Okay, so we call those our mole ratio, our coefficients. All right, so the Chemistry Cafe cook has a loaf of bread which contains 33 slices and a package of cheese which contains 15 slices. He's making sandwiches that have 2 pieces of both bread and cheese. Okay, so 2 pieces of bread, 2 pieces of cheese. How many sandwiches can he make? Okay, so if we need 2 breads and 2 cheeses for each one, well, if we have 33 slices of bread, oh, that was bad, and we divide that by 2, well, 33 divided by 2 is going to be about, what, 16.5, right? I think I did the math right. I'm getting my calculator because my brain is not functioning right now. Yay, I'm correct. All right, so we can make 16.5 sandwiches, but guess what? We don't want a half a sandwich, so we can make 16 sandwiches. All right, well, with our cheese, we have 15 slices. We need 2 on each sandwich, right? So 15 divided by 2 gives us 7.5. But remember, we don't want a half, so we can make 7 sandwiches. So which one can we make? Can I actually make 16 complete sandwiches? No. I would have 7 complete sandwiches, and then I would have 9 bread sandwiches. Does not sound appetizing to me. Sorry. All right, so a tricycle factory gets a shipment with 400 seats and 600 wheels. How many tricycles can it make? Okay, now we're going to assume every single one of the wheels is the same size, and we're going to assume that all of these wheels here are the same size. I know they're not, but that's okay. We're going to assume. All right, so for one tricycle, let's write out our chemical equation. One tricycle, we would need, well, let's do it. No, we're not going to break it down. Okay, we would need 3 wheels, and we would need 1 seat to make one tricycle. All right, so 3 wheels, 1 seat to make one tricycle. It says that we have 400 seats, so we have 400 of these things. We have 600 wheels, and they want to know how many are we going to make here. Okay, well, 600 wheels, each one gets 3. That would give us 200. Right? We have 400 seats, though. Let's make 400. No, you're not going to be able to make 400. Okay, why? Because you can only make 200 complete ones, and then you'd have 200 seats left over. So how many tricycles can you make? 200. Okay, do you see what we're doing so far here? All we're doing is we're applying what you would normally do in any situation. This is actually stoichiometry. It's just not with chemicals. So it's easy, right? Well, so is stoichiometry. All right, so how do we use stoichiometry in chemistry to figure out our answers? So we've got the same chemical equation here. It says how many moles of H2O are produced if you have 0.176 moles of O2 that are used. Okay, well, just to make it easy, we look at our mole ratio. First, we have to balance the equation. So if it's not balanced, the first thing you need to do is balance it. Okay, we're lucky. It's already balanced. Right? It says how many moles, so we're looking for moles of water, and we know that we have 0.176 moles of O2. Okay, so we're going from moles of O2 to moles of water. Okay, now we can use this, and we can do dimensional analysis to set this up. We start with what we have in the problem, 0.176 moles of O2. And we multiply it by a problem. Well, we have moles of O2, so we're going to put moles of O2 down here on the bottom because we want that to go away. And we want to go to moles of H2O. Well, nice thing about moles is that you can compare moles of one thing to moles of another because it's the exact same thing. 1 mole of oxygen is 6.02 times 10 to the 23rd particles or molecules of oxygen. 1 mole of water is 6.02 times 10 to the 23rd molecules of water. So it's the same thing. You can compare them one to the other. It's a glorious, wonderful thing. That's why we use moles. That's why I've tortured you with this so far. Okay. So how does this work? Okay, well, we would take our number that we set up here, multiply it by a fraction of moles over moles. Well, guess what? This is your mole ratio. So your moles of H2O, we go to the balanced equation. How many moles of H2O can I make? I can make 6. How many moles of O2 do I need to make those 6? I need 5. So here is where we put in our mole ratio. Okay, so now all we have to do, if we have moles of O2, they cancel. We're left with moles of H2O, and that's what we want in our answer. So now we set up our equal sign. We put moles of H2O here, and now we just do our math. It's that simple. All right, so 0.176 times 6 divided by 5. And we get 0.2112. We need 3 significant figures in our answer. So we're going to go to 3 significant figures. The 2 does not make the 1 change, so 0.211 moles of H2O. Okay, now do you see why I said you need to keep track of the compounds? Because now we're changing from compound to compound, and you have to be able to keep track of them. Okay, that wasn't so hard, I hope. Let's try another one. All right, same equation. Yes. How many moles of NO are produced in the reaction if 17 moles of H2O are also produced? Oh, look, we can compare reactant to reactant. We can compare reactants to products, and we can compare product to product. So we're going to find how many moles of NO, and we're starting with 17 moles of H2O. So 17 moles of H2O, starting off with, multiply Moles of H2O goes on the bottom. Moles of NO goes on top. And we can change from one compound to the other as long as it's moles. We can't do grams, but we can go from moles to moles. We can't go from grams to grams. That's why you have to go from grams to moles and then change to moles and then go back to grams. I know, it's just going to get more and more complex. It's an awesome thing. I love it. Okay, moles of NO, there are 4. Mole ratio, right? Mole ratio goes here. All right, moles of H2O would be 6. So we put 6 on the bottom. So 17 times 4 divided by 6. And you should get 11.3333 repeating moles of NO, because moles of H2O cancel. Okay, how many significant figures? We want 2. So 11 moles of nitrogen monoxide. All right. Uh-oh. Here it says how many grams. Am I starting with moles? Okay, well, can you go from moles of one thing to moles of another? Yeah, you use your mole ratio, right? And you go from moles of one thing to grams of that same thing? Yes, you know how to do that. So I want you to pause this, try it, come back and see how you did. All right, we're looking for grams of H2O, and we know we're starting with 1.9 moles of NH3. And where it says excess oxygen, that just means there's more than enough oxygen. We don't have to worry about it right now. We will eventually, but not right now. All right, so we're going to start with 1.9 moles of NH3. We need to multiply that by a fraction. We got to get rid of moles of NH3. We need to go from moles of NH3 to grams of H2O, but we can't go from moles to grams. Right? Remember that little thing I had? Well, no, that's not going to help you. That's okay. We can't go from moles to grams. Moles of one thing to grams of another. We have to go from moles of one thing to moles of the other thing. Right? How do we go from moles to moles? We use our mole ratio. There's 4. Coefficient for NH3 is 4, so that goes in front of the NH3. Coefficient for H2O is a 6. Okay, moles of NH3 cancel, but we're at moles of H2O. We want grams. We got to keep going. All right, we need to get rid of moles of H2O. We want grams of H2O. Okay, this should be looking familiar. What number always goes in front of moles when we have it in a fraction like this? 1. And then grams of H2O, remember that's your molar mass, so it's going to be 18.02. Moles of H2O cancel. Now we have the units we want, and now we can solve. So 1.9 times 6 divided by 4 times 18.02, and you should get 51.53, nope, 357 grams of H2O. We need 2 significant figures, so it'll be 51 grams of H2O, and that's your answer. Yay! All right, how many grams of O2 are required to produce 0.3 moles of H2O? So go ahead and pause it, try it, come back and check your answer if you think you got this. All right, so we're starting with 0.3 moles of H2O. We got to get rid of moles of H2O, so let's get rid of moles of H2O. We want to go from moles of H2O to grams of O2, but we can't put grams of O2 up here because these are different. So we have to put moles of O2. All right. The only time we can have this compound formula different is if we've got moles. Here, moles in both. All right, so we put a 6 and we put a 5. Moles cancel. And then we want to get rid of moles of O2, and we want to go to grams of O2. 1 mole and 32.00. Moles cancel. Okay, so 0.3 times 5 divided by 6 times 32 gives us 8. That's what I got. I hope it's right. All right, there we go. And there's one more left over. It says how many grams of NO is produced if 12 grams of O2 is combined with excess ammonia. Remember, excess just means there's more than enough. You don't have to worry about it. Okay, so I'm going to work this out. I'm actually going to pause it this time, but I want you guys to pause it. I want you to work it out and then come back and check and see what you got. Okay, this is how I set it up. So go ahead and pause it again so you can check it and make sure that you set it up correctly. All your units are going to cancel. We need, except for the grams of NO, we need 2 significant figures, so it would be 9.0 grams of NO. Okay, and that's it. I know we went through this quick, but I'll be able to make sense of it in class. See you tomorrow.